Okay, welcome back, everyone. So for this portion of the afternoon presentations, we're going to have Professor Barish. He will give us a preview of the talk he's going to give later at the public lecture. So that's gravitational waves, unraveling the mysteries of our universe. He will also be sharing with us his vision of the new Cosmology Center at UCR that he'll be establishing here with our fellow physics and astronomy faculty. Please join me in welcoming Professor Barish.
Oh, that's it. Okay, that's what I want. Okay. Okay, a lot of bright lights. I'm going to be talking later about the discovery, what it took to make the discovery of gravitational waves and put it in perspective a little bit in a separate talk. So my talk right now, which is going to be fairly short, I hope, is to put in context what we're trying to build here at UCR and why, kind of what's going on. And you keep hearing the word Center for Cosmology or Cosmetology or something. Anyway, the idea I'll try to give you here and maybe a few facts, and then you're going to hear from the new faculty, the faculty we've incorporated in the last 3 or 4 years to start building this effort. And this is kind of in progress effort, and so you'll get a vision of what we're trying to do. Anyway, what I am trying to illustrate in this first slide is how we're going about, which is a little bit new, unraveling, if you want, the mysteries of our universe. And it's in the past when we've had physics problems, it's usually, or astronomy problems, it's usually a fairly straight line from having the problem and some technique to understand it, a bigger telescope or a particle accelerator and so forth. This effort's a little different than that. The idea here is based on kind of a long history that some of us have had of seeing that there's a set of problems that have kind of fallen, not exactly between the cracks, but aren't identifiable necessarily in the mainstream efforts that are being pursued in physics or in astronomy. Maybe a fault of the fact that we, in most departments, have a department of physics and a department of astronomy. And there are many problems that kind of fall in between or overlap here and there. And although we do those, and people in astronomy do physics and people in physics do astronomy, kind of concentrating on this area, there, in our belief, is a lot of really progress and fundamental science that can be exploited by actually building an effort in this area. It's tricky because it's a little different than building an effort in some area where everybody is doing something directly related to what the others are doing, but maybe a different part of that. Instead, here, the overall effort is understood. It's kind of an umbrella of efforts trying to exploit some fundamental problems that fall between physics and astronomy. But the techniques are very, very varied. So what we're doing is putting together a set of young experimentalists that work in different areas where if you just look at that one, the other one looks like they're doing something rather different. But altogether, it adds up to this effort or this synergism where we try to pull together answering some of the questions about the universe. So let me just try to put that in perspective for a few minutes, and then you'll hear directly from our young faculty. So on the top, I show a picture of LIGO. That's gravitational waves. I'll talk about that in a couple hours. And also, John Richardson, who's one of the faculty members you'll hear about, is working on gravitational waves. So I'll talk about the problem of gravitational waves and what it took to discover it, what the challenges were and what we've done. He's working on where we go from where we are now because opening this opens up a completely new way to look at the universe. So that's the first subject. The second is the cosmic microwave background. That was mentioned in the previous talks, or even talked about somewhat. And our present best way and only way to directly try to see what happened in the universe at very early times is to explore, or is to measure with rather challenging new techniques and observatories what's called the cosmic microwave background, which will be described to you soon. And that is a kind of a photograph of what the universe looked like 400,000 years after the Big Bang. And so that is our newest faculty, Steve Choi. He's just starting to set up his labs here, and he'll tell you about that subject and what his ambitions are. And then in the lower right is one of a whole set of probes that are being made to try to understand this mysterious feature that the universe is made out of, not just what we know about from telescopes and other things, but what we call the dark matter. And the dark matter isn't defined well enough to give it some fancy name, or when we do, it turns out to not be the dark matter, we look for it. So it's a very challenging problem. But one of the most important problems we have in astronomy or in physics is to understand what the dark matter is. And Shawn Westerdale, this is one of his experiments, is working on the next generation experiments to do that. So let me reflect just a little bit. If we talk about modern astronomy, so the early stages in something, the birth of modern astronomy started with this guy over here, Galileo. And of course, astronomy went back way before Galileo, but Galileo represented the first time that we looked at the universe or looked at the stars, and not just with our naked eye, but with something that gave us more information. And so in 1609, he took the fact that that we knew how to make glasses at that time, because people needed glasses. They knew how to grind glass well and make glasses, and he took the fact that also somebody had developed a telescope at that time and made a 20-power telescope, and basically then immediately took it and he looked at Jupiter. And so we have all looked at Jupiter. You can see Jupiter. He looked at Jupiter, and what he saw was that Jupiter had 4 bright objects near it. And he assumed those were stars. And so he came back the next night or a couple nights later, and he looked again at Jupiter. And if they were stars, they would have moved in very different locations because they're not linked to Jupiter itself. They just go where they want to go relative to Jupiter. And what he saw instead were they were, all 4 of them were close to Jupiter. And they may have moved in their location, but they were close to Jupiter. And so that was the discovery of the 4 moons of Jupiter, the most famous discovery then by Galileo. Now we know there's more than 100 if you actually count little bodies and so forth near Jupiter. So that represented a milestone as the first time people really did astronomy with instruments. And we've gone through 400 years of astronomy roughly since then, a little more. And astronomy has progressed fantastically by the improvement of the instruments. So in a sense, the discovery of the 4 moons of Jupiter by Galileo is parallel to what I'll talk about tonight, and that is the discovery for the first time of gravitational waves that come from outer space. And then the work that's being done for the future that John Richardson will talk about, one aspect of it that he's working on, is building the new instruments like since Galileo that have exploited astronomy. When you move to the future, you have to figure out the right new instruments, and that's always a puzzle. You can go in many directions. Improving things is easy. Being clever enough to improve it in the right direction is really the challenge. And so we can reflect again on what happened in astronomy. So astronomers, as I said, have been looking at the sky with instruments for 400 years. The big change in astronomy came about less than 100 years ago when people started looking at the same phenomenon, or the same object in astronomy, but looking at them in different frequencies or different wavelengths. So originally, Galileo looked at the visible light that we can see with our eyes and did that with the telescope. But the big advance, in my mind, that has advanced astronomy so spectacularly in the last century has been looking at the same kind of objects, but in different frequencies. I show here kind of the everyday way we use different frequencies, but basically in astronomy, you want to, again, look at the same phenomenon or the same object, not just with visible light, but in the infrared, the ultraviolet, X-rays, gamma rays, and so forth. And so that is really, in my mind, the step that took it. And basically, as a scientist, it's envisioning that that's the way to get new information. In this case, that comes about because, of course, if I look at the same phenomenon, in this case, I look at this particular object, and you look at it in different frequencies, you learn different things. The different frequencies may give you different temperature information or other information. And this just shows the same object, this object here, looked at in the X-ray, just with X-rays, looking at it with the infrared, looking at it with radio waves, looking at it in the optical. And you can just see, without thinking about it, they're very different, and they're going to give you very different kinds of information. And so that's basically what has happened in astronomy with one, let's say, appendix to it all, which is starting in this century. And that is what I would call combined instruments instead of combined frequencies. And that was basically done very cleverly by a group of scientists who built nothing. They just took the fact that there are instruments around the world and that they would use them in a different way. In this case, radio telescopes. So this map shows radio telescopes around the world. And they managed to approach the people that were in charge of the set of the principals and set of the different radio telescopes and asked if they could use their data. And these telescopes were never being made with anybody having the vision of using them together. But this group basically took the hard job of taking the data in whatever form it came and analyzing it in a way that they could take the 7 telescopes where the data came from that were spread around the world and make it act like one radio telescope the size of the Earth. And by having one radio telescope the size of the Earth, they were able to image, and people saw this even on the front page of the New York Times, a picture of a black hole, which is called M87, where this is the outside of the black hole. And this was a spectacular development, even to be on the front page of the New York Times, and just, again, is combining instruments, which is a new, clever way to do this. This same group, who I kind of consult with, accidentally, kind of because I decided to learn about this to teach it in my class that I teach here at Riverside, they basically are improving the instrument by adding judiciously some more radio telescopes around the world, are hoping to do this. They haven't gotten funding yet, but I'm sure they will, in such a way that they can reduce the time between pictures so that in their terms, they're going to make movies instead of stills. So when you see this picture, you'll see its evolution. The surface of a black hole is predictable or testable in terms of some of Einstein's theory of what happens near a black hole. So we can envision that happening probably in the next 5 or 10 years. So similarly in physics, so I've talked about the evolution of astronomy kind of, but in physics we can go back to 100 years. And the main thing in talking about the kind of physics that was talked about in the first 2 talks started with Rutherford in the early part of the last century, and he had a picture of what the atom was. That picture is no longer our picture of the atom, but it had a big plus charge in the middle and the minus charges around it. And that's evolved through understanding quantum mechanics, scattering particles, all different instruments up until we have a big accelerator like you heard about earlier, that's the CERN accelerator, into a picture that's totally different than Rutherford's, and the fundamental building blocks are now what we call quarks. They're shown here with these little wavy lines between them because they exist inside of a proton, but can't come out outside, which I won't talk about, but it's one of the mysteries that we have, or one of the things that we have to explain. So we now have a rather different picture of the atom, or the fundamental constituents that make up matter, which has come about by a set of complex instruments, but a whole set of different ones, including the kind which are very different that detect neutrinos, like you heard about in the last two talks. So I'll take an example to show that these expertises, or understanding them, or the fields, intersect each other in a way that you have to put them together to understand the science. So if we take something that's kind of familiar, like a star or our sun, and ask what we understand or how we understand the star or our sun, then we can learn about it, how they're created, what their properties are, and so forth. That's basically the subject of astrophysics. And we know a lot about it. A lot of observations are made, and there's a whole science of astrophysics and understanding and probes and so forth. Second question, which is more fundamental physics, and it was talked about a little bit by Cheng Qi, is the burning of the sun itself. And that happens by nuclear physics. And it's completely something that we didn't know, we have only learned about in the last 50 years. I think it was proposed that burning how the burning of the sun happens in basically the fusion process 50 years ago or so. So to understand the sun, you have to understand astrophysics, nuclear physics. The emission of the neutrinos, which we heard about a little earlier, is particle physics. The fact that they do what they do, change identity as they come to the Earth. And then there's another one, which was also briefly mentioned, that stars don't have an infinite lifetime. They burn up the fuel that they have in the fusion process, and they collapse. And when they collapse, that gives a supernova, and understanding the supernova gives us a lot of information, including information about general relativity and so forth and so on. So one can see that all these subjects kind of come together, so there's a marriage of these that give us what we want. And that's built into what we're trying to do. So basically, looking at this Venn diagram, we're trying to build something we call the experimental cosmology group here, for no better name. But it's basically the merger of all these fields, which has tentacles that come from other fields that surround it, like high energy physics or nuclear physics, astronomy and astrophysics, and even tabletop kinds of experiments, atomic AMO experiments. And so the focus of our effort here is to take areas here that are going to give us the best kind of information about these merged fields that cross physics and astronomy, and where there's maybe instruments being made in the world that we can make an impact on. So an experiment that we'll hear about next from Steve Choi is the instruments being made to look at the cosmic microwave background signal. Better instruments are going to be made in the next generation, and he's developing technology that can go into those instruments. And so that's experimental cosmology, gravitational waves. We'll hear from John Richardson about what he's doing, which is basically very fundamental limitations we have in the present instruments, where we're now detecting, we think we're doing really well. We detected gravitational waves. I got the Nobel Prize in 2017. It's less than 10 years since we detected them. we now see some example of a gravitational wave every other day, roughly. But we want to do real science. We have to get to where we can do much, much better than that. And he's working on that, and he'll tell you a little bit about it. And then there's finally the areas that overlap fundamental physics and astronomy and astrophysics, and certainly dark matter is one of those, for example. So we're basically trying to build a center where we're not picking on any particular thing, where we're picking individuals. They have overlapping interests, and we want to build this into something where locally important work can be done that'll influence the next generation, where the people from here can play an important role in that without having huge physics groups and so forth that are running these big experiments. So the reason to create it here, other than the fact that we started from this idea, is that UCR has a lot of ingredients that are perfect for this. First, it's a Hispanic serving institution which solves and helps solve the problem of bringing other new, fresh kinds of people into the field. And so we help to bring an element of our scientific population that we're training into the forefront of discovery in physics. We are very good here at involving undergraduate students in our research labs. It's ideal in a small university with small groups and laboratories that the students don't get overwhelmed. They can come and work on forefront instrumentation in the laboratories of the people you hear after me that are developing important instrumentation to go into future experiments. And so we have about 50% of our majors do research, which is not typical of all universities. The establishment of these labs on campus, which is really built into our idea, really makes things happen here rather than just being participants in some big facility being done somewhere else. And it's kind of at the heart of what we're trying to do. And we already have some beginning of this, and it's involving undergraduates, graduate students, postdocs, and so forth. And this, having it as a center, it can provide then support for students, and I'll talk a little bit about the kind of support that we need and what we might do with it. So just in terms of not where the money come or the resources come from, but what we can do even while you're building such a center, I kind of divided it up here in the small gifts or grants or startup funds, whatever it is at the level of tens or $100,000, could enable us to do a lot of different things. First, to directly support undergraduate student support, whether it's individual or training grants. It'll help us do something that's absolutely essential on the campus because it's a campus that hasn't been at the forefront of these things, and that's to modernize and enhance our laboratories on the campus, where we need to make them come up to the standards of the most advanced techniques that are being used in today's world. And we can support having visitors that can teach us things and that can enjoy being here or work with us, workshops and so forth. So at that level, any funding that we raise can be used very well to kind of support the development of the center. At the next level, then larger gifts, we'd like to be able to attract the best possible postdoctoral researchers we can. In my experience, the most effective researchers directly working on forefront physics are postdocs, because they've gone through graduate school, they've learned everything they can learn, and now they have time, they don't have to do a thesis, to dedicate themselves to doing the next thing. So our ability to support, and that's very hard to get funding to support, but our ability to support postdocs and even to support ones where we have enough endowment that they can maybe have a name and you can attract the best ones is a real strong lever on building a team that is really able to do the complex and challenging things that we want to do. Then there's areas just because we have an old physics building and so forth that we need to develop in order to be able to build things that might go into the large facilities. For example, a high bay area, which in principle is there but needs to be developed. And lastly, we would like to finally get this funded as a true center, maybe by the government, maybe privately, where it is a named center of some sort, and we can use it both in terms of its attraction and in terms of the resources that it has. So that's our idea. It's embryonic, as I said, although we have people, which is really good people you'll hear here next, which is really the key. And so as I said, the physics of the future for us is, you've heard Cheng Ki, but now next will be Steve Choi, and after him will be John Richardson, and then Shawn Westerdale, and they'll give you some idea of, in the short time they've been here, what they're trying to do here and what they are doing here and where it'll go. And so I'll stop here and we'll move on to, I guess, Steve next. I'm fine. There's a blue pointer.
Yeah, thank you. It's truly an honor to be here, to be able to celebrate this special occasion with you all today, and also to be able to tell you about cosmology, our work in it, studying the universe at the largest physical scales and longest time scales. And it's really incredible, as we just learned from Professors Barish, Jung, and McDonald, that we can build these intricate instruments and use them to test and experimentally learn something so fundamental about our universe. And as you could probably guess from this title slide, our work in cosmology, observational cosmology, centers on building these astronomical observatories and placing them at some of these most remote sites we can get to on Earth, such as the Atacama Desert in Chile, shown here at about 17,000 feet altitude, and using them to make precise observation of our cosmos and to learn something new about it. Let's see if this works. Great. So I'll just first show you this video as I describe how our current picture for modern cosmology has come to being. You're seeing this beautiful video of a lot of these galaxies flying through them. And I want to emphasize that's not a computer simulation, but actual images that were taken by the Sloan Digital Sky Survey. And we're just a small part in this vastly large universe with, here it's showing about 500,000 galaxies. And it wasn't until about 100 years ago that we just learned about this universe that we live in. It's expanding as we speak. And now we know, if you then ask what happened in the past, rewinding that expansion that's happening today, then you get what we call the hot Big Bang, a state of our universe that started from its much smaller, hotter, and denser state. We also know that our universe is about 14 billion years old, as we heard. And current best observational evidence for our picture for this hot Big Bang model is what's called the cosmic microwave background, the remnant photons that are left over from that thermal, hot, dense state in the early universe. So this is essentially, it's a temperature anisotropy map, so fluctuations in the temperature as measured by the Planck satellite. It's showing you these hot spots and cold spots that are at about plus plus minus 300 microkelvin after removing its mean temperature of about 3 Kelvin. And it's essentially showing us the snapshot of our infant universe when it was only 400,000 years old. And of course, 400,000 years is a long time in human time scale, but in the cosmological sense, where the universe is 14 billion years old, that's a small number. And so we're really looking at the baby picture of the universe where it was much simpler. And what's so profound about this image is that these temperature fluctuations are tracing the primordial density fluctuations that existed. This means there were more dense regions and less dense regions here and there. And it's essentially these inhomogeneities that are the seeds that grow into all of that rich structure that we just saw in the video in the previous slide. So our goal as cosmologists are to understand how the universe began, what it's made of, and how it evolved from the state from when it was 400,000 years old, where it looked much simpler, to the rich structure that we have around currently. And we can do this because our telescopes are like time machines. Because the light travels at a finite speed to get to us, the farther the objects we look at, the longer it takes for the light to travel to us. So we're essentially looking at these distant objects as they were when they were in their younger form. For example, these galaxies that are around us, the light from them could have been traveling for a billion years, or a couple billion years. But if we look towards the farthest point we can look at in our observable universe, we get what we call the edge of the observable universe, and the cosmic microwave background comes from this edge of our observable universe. And beyond it, the universe in its younger form becomes more opaque, and we cannot see through electromagnetic radiation, at least now, through this point. So again, we want to understand how the universe started and evolved from this state, just 400,000 years after Big Bang, to the current picture. And we need some formalism to be able to describe this. And here's just a single equation that I'll have in my talk, but it's a profound one, Einstein's field equations that relate matter to geometry of the universe. So for instance, you tell me how the matter is distributed, such as the example given here, the sun and earth, and I can tell you how the space-time is curved around them. Of course, the discovery of gravitational waves by the LIGO experiment, as led by Professor Barish and others, had given us some of the most fundamental evidence in support of the theory of general relativity. If we take this equation and apply it to the whole universe and ask how the dynamics of the universe evolves, given the content in it, we get these actually quite simple equations that can relate the dynamics and history to the content we have. And so we get this time evolution picture of an expanding universe where we're sitting here with all of these large-scale structure and galaxies and so on, to the earlier epochs where the CMB is coming from and where the first star was formed. And through a host of cosmological observations, we establish what we call the standard model for our universe. And it's a remarkably simple one that just has 6 free parameters, 6 numbers to describe it all. And we've heard already a few times about these contents, the dark energy, dark matter, filling in 95% of our universe, and only 5% constitutes what we are familiar with. And we can actually measure these contents through observations of the CMB, because again, the CMB is, the temperature anisotropy shown here, is tracing the primordial density fluctuations that existed in the early form of our universe. And if there's different amount of dark matter versus ordinary matter, then this actually changes the density perturbations, density fluctuations that existed in that early form, and thereby changing the temperature anisotropy in the CMB that we can observe today. The bottom line is that a range of cosmological measurements are pointing to one basic model that can, again, describe it all, which is 6 numbers, which is incredible. But despite this success, we're far from having a complete picture for our universe. Again, we can understand the expansion history given the content of our universe. So if we look at this, the CMB more closely and look at smaller regions, then we can actually tell that a 1 degree spot, the light could not have traveled farther than this black bar shown here until the cosmic microwave background has emerged 400,000 years after Big Bang. So it's like having some 40,000 independent spots of about 1 degree on the spherical shell that really did not have time to interact with one another, because nothing can travel faster than light, at least in vacuum, as we heard. But curiously, we see that these parts that are spread by such vast distances look exactly the same in statistical sense. Their statistical properties look identical, even though they didn't have any time to talk to one another. And so this is where the theory of inflation comes in. So perhaps this posits that perhaps our universe, the observable part of it, has emerged from a universe that was once much smaller, but that went through this rapid exponential expansion period, as indicated by this arrow in this timeline. And if such event happened, then the whole observable universe probably has emerged from the same spot that was able to talk to one another, giving rise to this isotropy, the homogeneous, the sameness that we can see in all directions. And this is a very profound theory that gives us the initial conditions in the density fluctuations that again eventually grow into all of the large scale structure we see. And this would generate, again, gravitational waves that would leave measurable imprint in the polarization of the CMB that we can observe today. But it's a tiny signature, tiny signal that we're after. We think it could be at the nanokelvin scale on top of a 3 Kelvin background. So in order to measure these, we need to build much more powerful observatories, like these shown here, called the Simons Observatory, a set of small aperture telescopes shown in the foreground, and a large aperture telescope shown in the background. This is a picture just from a couple months ago, so this is really work in progress. This is at the Atacama Desert site that I showed in the very first slide, at about 5,200 meters. So a tremendous amount of exciting progress happening in constructing of this next generation observatory. Another telescope called CCAT has been built and showcased in Germany just a couple weeks ago, and we hope to have this disassembled and shipped to this higher altitude site, again in the Atacama Desert. And going to this high altitude site, we get above much of the moisture in the atmosphere, and this gives us the best observing conditions to measure the faint signals in the cosmic microwave background. But at the heart of these telescopes, or the eyes of these telescopes, are what we call the superconducting detectors. And these are what actually drive the sensitivity of our observatories. As you can see in this progression through these different generations of experiments, we're trying to increase the number of detectors by an order of magnitude each time. Starting with a few thousand detectors, where I started as a graduate student, to the current generation Simons Observatory, CCAT Observatory, with which we are trying to field over tens of thousands of detectors, approaching 100,000, to CMB Stage 4 on currently envisioned ultimate ground-based experiment that will field over 500,000 detectors. And you can see the trend. And This is necessary because each of these superconducting detectors has reached its maximum sensitivity we can get. They're very mature, so the only way to get sensitivity is to field more of them. And the way we're tackling this problem is to develop a new detector technology that's shown here, what we call kinetic inductance detectors for CCAT, because this technology is allowing us to pack in more detectors than the commonly used, what we call transition edge sensors. In here, it's about 6 inches across, so we can fit twice as many detectors currently, and hopefully about 10 times more detectors in the future. To conclude, I'll summarize by saying we have this remarkably successful cosmological paradigm, the hot Big Bang model, but it's an incomplete one that we're trying to complete with more precise observations of the CMB. And we're trying to do this by developing more sensitive instruments for these new observatories with our work here at UC Riverside. And I'm excited to have started just last quarter building up my new lab and working with new undergrad researchers. So thank you and congratulations again to Professor Barish.
Next, we'll have Professor Jonathan Richardson from UCR.
Thank you, Shinwen. It is a pleasure to be here as well. So I've been at UCR for almost 3 years now. From my postdoc years on, I've spent it in the field of experimental gravitational wave detection, working first with LIGO. I first got involved through a postdoc fellowship at Caltech, which is where I first met Barry. And I came here 2.5 years ago to create a new experimental gravitational wave group, the idea being that it would both contribute to foundational technological R&D, both to enable future upgrades of the current LIGO facilities, as well as foundationally contribute to the design and the planning of the next generation successor experiment in the US, which is this concept known as Cosmic Explorer. It essentially is a 10 times larger LIGO. So my one real equation that I'll show here, the details don't matter, but Steve's talk actually gave a very nice overview of relativity, a good introduction to this. He showed in the beginning of his talk a particular slide that showed a massive object in space, and it visually in a 2D plane illustrated the warping of space-time, the curvature around the presence of this mass, which is a prediction of relativity. And so gravitational waves, like illustrated here, would be the phenomenon of when those massive objects that are distorting space-time are accelerating. So the dynamics of that space-time curvature. So here, for example, are two binary objects. These could be black holes, for example, two massive objects. Each one is individually distorting this local space around it. And so you can see if we have an orbital binary system like this, they're continually accelerating. And so the effect is to depress space-time under the mass. It effectively relaxes once the mass moves around its orbit. And so the effect in the far field is this train of rippling distortions in the geometry of space-time itself. And so that physically is the effect that LIGO is just beginning to detect. So this equation, if you solve and work through the field equations of general relativity in a linearized approximation, which would correspond to us here in the distant far field, this is the signal that LIGO is physically measuring. We call this concept strain. And so strain is the fractional stretching of space-time, the distance between 2 points separated by some distance L. So it's the delta L over L between these 2 points in space, due to the passing of this gravitational ripple. And so in this equation, you have a source term here on the right to produce this signal, which requires the presence of some mass 1, and the second dot indicates a time derivative, so you have to not just have a massive object, but it has to be accelerating. So a binary system is a key astrophysical system that satisfies this criteria. And this is related by a coupling factor here that effectively relates the presence of mass energy that's accelerating to the amount of space-time curvature you get, which LIGO detects. And it scales as these natural constants of the gravitational constant over the fourth power of the speed of light. And so if you were to put numbers to this, the coupling factor is on the order of 10 to the minus 44 meters of space-time stretching per joule of energy. So it's an incredibly faint effect because of this coupling. This was the reason that Einstein famously wrote that gravitational waves, while real, are of no significant consequence because they're so faint they'll never be detected. So when a gravitational wave actually passes through the Earth, LIGO at its core actually uses a pretty simple experimental concept to actually detect the presence of these passing distortions in space-time. It uses this device that originated in the late 1800s called a Michelson interferometer. And so the idea here is you have some coherent optical source. In LIGO, it's a 1064 nanometer laser that passes through this optic we call a beam splitter. It passes 50% of the light in transmission. It reflects the other 50% of the power. And so it travels down two paths and hits distant end mirrors and bounces back. And so the effect in the far field of gravitational wave actually passing through the plane of the Earth. So if we had, say, our binary source orbiting directly overhead, the distortions would pass through the Earth in a way that create this characteristic stretching in the x direction and contracting in the y direction. And as multiple wave cycles pass through, that oscillates. And so fundamentally, what this interferometer is doing is comparing two light clocks. So we know light travels at a constant speed, so the light travel time down and back to the beam splitter just depends on the distance. And so the effect of this differential stretching is what actually produces the measurable signal. So if I zoom in now just on what we call the readout port or the antisymmetric port of the interferometer here, these two beams, these two light clock fields are actually being interfered with each other. And so this is depicted here visually. This would represent, say, the two electric field amplitudes of the two laser beams in the two arms. And so as you get this differential stretching and contracting, you get this shift where you alternate between perfectly constructive and perfectly destructive interference. And so when this is stabilized by a linear control system, the amount of power that you actually read out here in the interference beam is directly proportional to the arm length difference, so the stretching of space between the two interferometer arms. And so as someone mentioned earlier, the physical scale for this actual stretching that LIGO is detecting, is about 1/10,000th of a proton diameter, measured over a 4-kilometer distance. So most of the sources that LIGO has seen have almost exclusively been the mergers of two black holes in the distant universe. And so this is a template reconstruction of the very first detection that LIGO made. And this is strain here. So this is the delta L over L that I showed, the left-hand side of the first equation I showed. So this is the physical signal, the physical stretching and contracting of space-time along the two interferometer arms. And so you notice it's this characteristic oscillation as these two black holes are orbiting each other. But because of relativity, because of the existence of gravitational waves, orbital energy is being lost continuously through the emission of these gravitational waves. They carry energy, they extract it from the binary system, and so the binary separation starts to get closer and closer. And as it does, because of conservation of angular momentum, it has to speed up. And so that's why we see this characteristic increasing in the frequency of the sine wave until eventually it hits a peak, it merges, and then exponentially decays in what we call a ring down to a newly formed black hole. So if we take this signal and we were to plot it as a function of time in frequency space, the frequency of the sinusoidal oscillation starts with some very low hum, and then it very quickly rises just as the black holes plunge and finally coalesce. So this was the physical signal that LIGO first detected, and we've seen about 100 more of them since. And what I'm going to show now is a physically accurate numerical relativity simulation of this event. So these are the two progenitor black holes. The warping of space-time that we see here is causing this lensing of the distant background stars and galaxies. And so these are orbiting in spiraling, losing energy to gravitational waves. So they're speeding up, they eventually merge, and then they settle to a quiescent, newly formed black hole. So that's LIGO to date. We're detected to date about 100 of these events. And so the question now is where do we go from here? And I would argue the field right now is on the very cusp of transitioning from a basic discovery phase where these are just detected and general relativity is confirmed for the first time at a very deep level, to an era of precision science where we're both detecting these events all the time, hundreds of thousands or to millions of these events per year. And local events that LIGO is seeing now will measure with incredibly high signal to noise, which will allow completely new, potentially revolutionary tests of fundamental physics. So shown here is an artist's conception of the next generation facility to succeed LIGO in the United States, which is known as Cosmic Explorer. The baseline plan is to make it 10 times longer than LIGO, so a 40 by 40 kilometer long interferometer. And the goal is to reach 10 times higher strain sensitivity than the next upgrade of LIGO. And this 10 times target in sensitivity is not arbitrary. It's motivated by the fact that it allows us to access most of the observable universe. So this figure illustrates what we could hope to detect with this next generation experiment, Cosmic Explorer. And so for reference, these are the events that LIGO has detected to date in the first 3 observing run. Here are some of the most famous ones, including the one I showed an animation of down here. So on the y-axis here is what we call cosmological redshift. This is a quantity that is proportional to the amount of look-back time. So higher redshift is an earlier time in the universe. It's not a linear relationship, so I show on the right-hand side the corresponding physical age of the universe. So going from near its present age back to around the era of first star formation, and we see that CE will even see beyond that. So in an astrophysical context, based on our understanding of astrophysics and on the first detection of LIGO events, based on their event rates, this is the estimated population of stellar mass black holes and neutron stars in the universe that we could hope to observe with future detectors. And so notice that these events that LIGO is just barely resolving with a signal to noise of 8, down here would be detected by a next generation detector with a factor of 1,000. And then beyond accessing the entire population of known black holes and neutron stars, we'll also be able to detect the so-called population 3 stars. So these would be the earliest stars that theoretically formed in the universe, very low metallicity stars, the stars that created some of the first heavy elements in the universe. And then if they exist, more exotic sources like primordial black holes, which could be one explanation for dark energy, at least in part, would be detectable to this new detector as well. So within this mass range that we can hope to detect sources in to Earth, Cosmic Explorer really would be the ultimate experiment that can see every source there is to see in the observable universe. So with all these detections, which we expect would number in the hundreds of thousands to millions per year, there is a wealth of precision science that can be done with this on many fronts. In cosmology, this will be a precise tracer of the cosmic expansion history of the universe, and in a way that is complementary to existing techniques. It will also allow extremely high precision tests of the dynamics of strong field relativity and of proposed quantum gravitational modifications at the event horizons of black holes. And it will allow us to also probe the interiors of neutron stars, which is where there exists the densest states of nuclear matter in the universe, conditions that we couldn't come close to replicating in a lab on Earth. So, just briefly talk a bit about some of the technical problems that limit us. So what does it take to get from where LIGO is now to the edge of the observable universe? Well, I'll start with a diagram similar to what I showed before. So this is a Michelson interferometer where the laser again comes in. It splits in two directions, X and Y, and then recombines at the readout. And that is the core of LIGO, but there are a lot of additional optics overlaid to actually reach LIGO levels of sensitivity. And so if I add that additional complexity, this is actually what we have. So there are additional optics that filter the input beam. We have what's called a power recycling cavity here to build up the injected power. We have an output side cavity that allows us to filter the frequency response of the instrument. And then the core of the interferometer here are these two 4-kilometer long arm cavities. So these are made up with two mirrors, which are known as test masses. Here's a picture of one of them here. They're 40 kilogram suspended monolithic pieces of fused silica glass. And in order to achieve these cosmic explorer levels of sensitivity, we need to suppress the quantum fluctuations of the laser light that bounces off of these mirrors and is used as a probe to interrogate their positions. So to do that, one of the key requirements for next generation experiments are very high levels of laser power. So we need 1.5 megawatts of laser power to reach the sensitivity targets I showed in the last plot. And the challenge of that is LIGO is nowhere near this level of operating power now, and it's limited by the fact that even the best mirrors in the world absorb some of this laser power, and they thermally distort in several different ways. And this actually limits the sensitivity across most of the frequency band of signals that we can access on Earth. So my group at UC Riverside is working at directly addressing this very limiting fundamental problem from the experimental side. So we're trying to develop new types of adaptive optics that counterintuitively can correct the heating of a laser beam on these test masses by building these devices that projects infrared radiation onto other parts of the mirror. So we correct thermal deformations by adding more heat, in essence, but with a spatially different distribution than the laser beam heating. And so we've developed this new technology over the last 2 years that allows us to build these devices with an internal infrared radiation source, which is extremely stable. And we chose infrared because almost 100% of the infrared is absorbed by the bulk fused silica substrate of the test mass. So 100% of the power effectively is absorbed. And so through clever non-imaging optics designs, we can create intensity patterns such as this, or in the future, even more complex patterns that allow us to very precisely control the mirror curvatures and create lenses inside optics and LIGO to push the interferometers to higher levels of power and higher quantum limited sensitivity. So the concept I showed of the first prototype has just been built in the last few months after about a 2-year design and fabrication phase. This was assembled in the lab in the physics building here. And so these are the two halves of the reflector that come together with some electronics mounted in the center in between. This project has really heavily involved students at all levels. These actually are 2 undergraduates in the group and a graduate student here in the back. And then shown here on the right is the assembled prototype, ready for tabletop testing. So in the last few months, we've completed all the testing that could be done here locally in our local lab facilities. And this has now gone for final testing in the LIGO Laboratory Engineering Labs at Caltech. So this was delivered there about a month and a half ago. This is it sitting in a large vacuum chamber, which you see here. And this is an actual 40 kilogram LIGO test mass now being installed for this part of the experiment that will sit just behind this. And we're setting up an optics experiment here that will actually directly measure the effect on the test mass. So, as I mentioned, this has created many opportunities for about 10 undergraduate students and several graduate students and postdocs as well. And I'd like to hand next off to one of those students, one of the graduating undergrad seniors from our group, Peter Carney, who will talk a little about his experience in the group. Peter.
Nice talk. Can you click forward? Can y'all hear me? Oh, these lights are kind of bright, I'm not gonna lie. Before I formally introduce myself, I am a senior undergrad in Dr. Richardson's lab, and it's a great honor to be here today to speak to all of you here. And a lot of you guys have mentioned about, pipelining students in UCR to, have good careers and training in science and stuff like that. And we're having our current young faculty lead these research to get our new students to be in these pipelines to have more experience. Well, I am a benefactor of that new pipeline. So from me to you, welcome. I am the next generation. And I will be talking about my experiences as an undergraduate here at UCR, and specifically in Dr. Richardson's lab. Okay, so I kind of want to give you guys more of like a story time type of deal. I'm not really gonna talk too much science. I'll save that for like the big wigs and stuff. But first off, I started working in Dr. Richardson's lab in 2021, so I was barely going into my second year. We had just came back from COVID, and right off the get-go, I started off with a lot of experimental experience. I was building a visible light optical cavity, as you can kind of see right there on a tabletop scale. And then I was also helping him with the frosty work as well. So right off the get-go, I was exposed to a wide variety of experimental experience. And as for many undergrads in our department, for me especially, that pipelined me straight into an internship at Caltech for the summer of 2022. So as you can see me on my first day, I didn't dress that formally, but I was just really happy to be there. I was just very new to the whole process. I could barely tell you what a gravitational wave was back then, but it was nice. I ended up working for 10 weeks, got some good research results, and then I came back to UCR and I felt like I was a hot shot or whatever. I didn't know anything, but still felt like I knew some stuff. And so I not only kept working in Dr. Richardson's lab, I picked up a couple other strings of research, namely in particle physics. I'm thankful to say that it won me a nice scholarship for my research in LIGO. It was pretty nice. And then also around this time, I'll take a second to give a big shout out to the man of the hour, Dr. Barish. I took his class around this time, and when the man says that he loves teaching, he really does mean that, because at this point in my career, I didn't even know, before I went to Caltech, before I started any of this, I didn't even know if I wanted to be in research or go to graduate school at all. Much like Dr. Barish, I thought I had a career in sports. I thought I wanted to play basketball, and then I hopped in a research lab, and I was like, oh wow, this is kind of nice. And then once I finished at Caltech, I was like, yeah, I definitely want to live this life. This is a nice life to have as a researcher in science and stuff like that. So when I took his class, I really wanted to take it to try and figure out where to go in physics and what to do. And I was kind of intimidated, and so I talked to Dr. Richardson about this. I was like, hey, Dr. Richardson, and by the way, all of these faculty here at UCR, especially Dr. Richardson, very approachable, very approachable. And I was like, I don't know what I want to do. Do I want to go to particle physics? Do I want to stay in LIGO? Blah, blah, blah. And he was like, why don't you reach out to Dr. Barish and take his class? And I was like, what do you mean, just like cold email him? Like, I could do that? And he was like, sure, just shoot him an email, be formal, send him your resume or whatever, and say if you want to take his class. And so I not only reached out to Dr. Barish, but he was super kind. He allowed me to take his class as an undergraduate. And I think it was extremely influential in me figuring out where I wanted to go and what I wanted to do and stay focused in for my career long term. But despite that, I still did a few more stuff over the summer. Like that was my junior year. Now in the summer of my junior year, I ended up going to CERN. Many of you are familiar with for internship. Now, after a few years of researching through the wonderful program here at UCR, I can say that I've been to 8 conference talks, 2 of them international. I've been to 3 poster presentations, as you can see up there. I've been to 4 national labs, and I've been to both of the LIGO detectors. And this is all because of the wonderful opportunities that researching in labs at UCR can create for you. And so once I was like, okay, I think this is about it. Now let's see if I can apply to graduate school. I know I kind of want to stay focused in this field right here. And so I'm very happy to say that I will be attending Caltech for a PhD in this fall of this year. And so I guess the main point I want to drive is, like, how is it so significant in my life to research here at UCR, and what has it done for me and other undergraduates as well? Well, as I've already said, it's exposed me to a wide variety of skills and topics. I learned a lot about how gravitational waves work, how visible light cavity works, et cetera, and I think that a lot of undergrads in our lab have this opportunity to expand into different areas. And by expanding into these different areas and getting a wide variety of experimental research, not just experimental research, but some of the theoretical and simulation concepts, you find what you like and what you don't like. And so I found right away what I liked to do and what I didn't like to do. And that kind of gave me a more directionalized path and what I would want to keep doing after graduation. It gave me a lot of confidence to step into these internships that I've had in these last 2 summers, to not only succeed, but to have a smooth onboarding process. I think a lot of the things that undergrads in this department are very scared of is that they don't know enough to start stepping into these labs. I don't know anything about quantum gravity, or I don't know anything about general relativity. You don't necessarily have to know anything. I did not know anything when stepping into Dr. Richardson's lab, and I didn't know anything about particle physics stepping into a particle physics lab. But they'll pipeline you smoothly, and then that gives you more confidence to not only succeed in those labs, but to succeed in other labs and off-campus sites or jobs or whatever. And I think that's an extremely invaluable experience to have. And then on top of that, it gave me connections to lots of places. Dr. Richardson was just saying how we do tests at Caltech. Well, that's a very great way to get hands-on experience in these labs. Lots of other labs go to other national labs and stuff like that to do experiments. Again, very great way to do these experiments. And then as you can see, there's me. Shout out the homie Tyler and Dr. Richardson's lab. We were at LIGO Livingston. It was pretty hot down there that day, but you know, it was pretty fun. And then, of course, I can't just talk about myself because, I mean, our whole undergrad crew is like pretty amazing, right? So, I mean, and not just in Dr. Richardson's lab, but I'll start with them. Shout out the homie Aiden, who is also a very fantastic researcher. We don't want to talk about, we do a lot of undergraduate research and they do a lot of the legwork. He pretty much took almost the entire lead on designing and fixing and building that vacuum system. He's an expert now on vacuums. And he also is a very good expert on how the Frosty is designed and built. He did a lot of that legwork too. And where did that get him? Well, he's committed now to Stanford for a PhD. Shout out some of the other undergrads. You already saw this picture, but I'm gonna show it to you again. We got Cynthia, we got Luke, and we got Tyler in the back. Again, working on that Frosty right there. Shout out the homie Shane with the lab. We're at Caltech. She's only a 3rd year, so she's gonna graduate next year, but she's got a very nice internship lined up this summer. Also, of course, we're also great friends outside the lab too. Again, you can see us traveling, giving postering presentations, talks, and other things of the like. And this is just for this lab. I know I'm not gonna bore you with all the other students that do amazing things, like Josh going to Princeton or Jared going to Cornell or so-and-so going somewhere else. But what I can confidently say is that it's been truly an honor to not only have worked for Dr. Richardson, but to have him give me as much experience as he has. It's extremely invaluable, and it's pretty much changed the trajectory of my life. I would not be standing here today telling you all these cool things about what I've done and what these people have done if I hadn't stepped foot into his office the first day and said, hey, can I research for you? And I think it's very invaluable. And I'm very appreciative to Dr. Barish as well for being such an influential person in my life and helping me figure out where I want to go. So thank you guys, I appreciate you.
see, how does this work? The first challenge of an experimental physicist is if you can make your slides show up. Does this do anything? I'm supposed to press something to make the slides come up. So I study dark matter. You can see some of it right here. We found it, we're done. All right, so thanks everyone for having me here. Thanks everyone for being here. It's an honor to speak to you at this event. So my research is in the field of dark matter and neutrino physics. And you'll hear from me, Shawn Westerdale, as well as my postdoc, Michaela, and one of my graduate students, Alec, Peck. So the question we ask in our lab is, what is the universe made of and how did it get here? So in other words, if we're doing experimental cosmology, we're asking about the makeup of the universe. Yeah, so this is of course a question that goes back to sort of the dawn of civilization, where we first thought that everything was made of some combination of earth, fire, wind, water, and sometimes a fifth element, the ether. But then we found the scientific method, and we found that things are made of more constituent atoms. And at first we thought they were just a simple negatively charged electron circling a positively charged nucleus. And with this model, we were able to describe all of the elements that we now have arranged out in the periodic table just by changing the number of electrons orbiting the nucleus. Eventually, we discovered quantum mechanics and that the nucleus is composed of more fundamental particles, the neutrons and the protons, and this allowed us to explore the more complex structure of the table of nuclides and understand nuclear physics and how nuclei interact with each other. And by studying this in more detail, we eventually found that we can break our protons and neutrons down into more fundamental particles that we call our quarks, and our electrons belong to a class of particles known as leptons. And the interactions between all of them are carried out by these bosons right here, another class of particle. So this is what we call the standard model of particle physics, and it describes everything we see and interact with on a daily basis using this very simple and easy equation. I expect you all to memorize it by the end of my talk right now. So this model has been tested to extremely high precision by experiments out at Fermi Lab in Chicago and Brookhaven National Lab in Long Island and the Large Hadron Collider out in Geneva. And these experiments find that the model matches data extremely well. So this is a very successful model at describing the interaction of the most fundamental subatomic particles. But then what happens when we apply this to the also very successful model of cosmology that you recently learned about from my colleagues? Well, everything falls into chaos. So first, as you've already heard, the early universe, when matter is first being created in the Big Bang, our particle physics model says that we should always produce an equal number of particles and antiparticles, and they should annihilate with each other, leaving us with nothing. So let's perform an experiment to see if this model is accurate. Look around. Do you exist? Do the people next to you exist? Well, then our experiment shows that this model is wrong. Now, we don't know why, but some of our theory colleagues have told us that it's possible that an asymmetry between the behavior of the neutrino and the antineutrino might be able to explain the dominance of matter in the modern universe. Another problem is that the interaction between the standard model particles that we know and all of these forces cannot explain the level of structure that we see in the early universe when looking at the cosmic microwave background that you just heard about, or when we look at the layout of galaxies and galaxy clusters. Similarly, when we look at the dynamics of galaxy cluster collisions, or if we look at the way that spiral galaxies rotate, the forces and particles that we know about cannot explain what we observe. Now, all of these mysteries can be solved by introducing another type of particle to the standard model that we currently don't include, and this is what we call dark matter. So our observations all say that we need 5 times as much dark matter in the universe than we have regular matter, standard model matter. So everything that we've done, a great success is really 5% of here, and 26% is dark matter that we don't know how to fit into this big picture. So another problem that arises is that our standard model says that neutrinos should have no mass. But the fact that we observe them oscillating in flavor, as you've previously learned about, means that they have to have some mass, and we don't know how to include this in the standard model yet. However, a number of theories have arisen that might explain this. One of these is potentially another kind of neutrino called a sterile neutrino, which would also be a candidate for dark matter. And there are also dark matter theories that have a whole dark sector of particles, and the neutrinos might provide a window for peering into that dark sector. So the main focus of my research is in a technique called direct detection, and the idea here is that a large cloud of dark matter surrounds a galaxy, and as the Earth moves around the galaxy, we're moving relative to this cloud, creating a constant wind of dark matter particles constantly passing through us. So we build a detector here on Earth, and we wait for an extremely rare interaction where one of these dark matter particles scatters in our detector and makes a signal we can see. The challenging thing is these interactions are expected to be extremely rare, and so any signals that come from things that might mimic dark matter but are from the standard model will easily drown out the signals that we're looking for. As a result, we build our detectors deep underground so we can get away from all of the radiation from cosmic rays and actually run our low background experiments in very isolated environments. So one of the experiments I work on, Deep 3600, which is currently running, is over a mile underground in an active nickel mine in Canada. And actually the UCR group here, led by Michaela, my postdoc, is in charge of the analysis of the experiment now that it's running and has data. We're also working on another detector, DarkSide 20K, which is currently under construction out in central Italy under a mountain. So this has a 50-ton liquid argon target within a much bigger 650-ton muon detector that it tags background so we can get our low background results. So the UCR group here is in charge of this muon veto, this outermost detector, which is one of the major subsystems of the experiment. So actually, some of the undergrads in this group have been actively involved in building and designing parts of this experiment. Okay, we're also working on a further future experiment called DarkSide Low Mass, where we're the lead institution. And we're figuring out how do you design a low threshold detector to look for light dark matter candidates. And if we do that, can we put a similar detector near a reactor and measure the neutrinos that come out of it and possibly look for sterile neutrinos or probe into the dark sector? And also with some of the undergrads in my lab, we're currently looking into ways of taking this technology that we're developing for dark matter detection and seeing if we can develop new medical technology. And lastly, we work on the Dune experiment, which uses 40 tons of liquid argon in an abandoned gold mine out in western South Dakota to measure neutrinos produced at a beam in Fermilab near Chicago to see if the weird properties of neutrinos can possibly explain the matter-antimatter imbalance. And we're applying our techniques from dark matter detection to see if we can enhance the performance of these detectors and look for exotic dark matter candidates. So here, Michaela, you can take over.
Okay. Hi, I'm Michaela. The aforementioned postdoc for Shawn. I'm just going to give you a few details more on what we are doing here specifically. So I'm leading the analysis. I happen to be the analysis coordinator of the 3600 collaboration. And right now we are actually trying to perform the very first observation of the same reaction that is expected to actually to be used in the Dune experiment, and I can eventually extend the physics reach in DarkSide 20K. So we are aiming to observe neutrinos coming from the sun in argon, which will eventually give you an excited potassium, which gives you a cascade of gammas, so additional lights together with a nice electron, giving you eventually electron recoil. So that's a very unique signal. And we are aiming to perform the very first observation right this year, right now, here in Deep 3600. The experiment at the Snow Lab, you can see here, surrounded by his water tank to reject the cosmogenic backgrounds that Shawn was referring to. Now, also, thanks to the interaction with theoretical physicists, the same interaction that hopefully we will have also in the cosmology center that we are trying to build here at the UCR, we could also extend the dark matter search in Deep 3600. So instead of searching only for single scatter dark matter, you can also search multi-scatter dark matter candidates. These guys are not so shy as the usual dark matter, can give you even thousands of scatterings in your argon detector, and also they are very, very heavy. Fun fact, when we published this analysis in 2022, other experiments did the same kind of search, multi-scatter signal in not only argon, also xenon, also solid state dark matter detectors for the very first time. We kind of set a trend, if you want. We did that for running detector, and I expect this happen for future detector like DarkSide 20K. DARSAI 20K is going to be built in Italy, in Laboratorio Nazionale del Gran Sasso. If you're wondering, I'm Italian, so that's why I can tell it easily. This is going to be built under a lantern. And as Shawn said, we are responsible of the outer veto here. So you have the true detector, if you want, where you expect dark matter surrounded by a bath of 650 tons of liquid argon, additional argon, which will work, as we're going to see, as a shield, a specific shield, actually. So dark matter, if you're lucky enough, will give you a signal in the detector, right? If you're lucky. Not yet, so far. But we still have particles which are produced due to the interaction of cosmic rays with the atmosphere, about 30 muons per meter square per hour, hitting our detector, even if we went underground in a mountain to have some shield. Worked enough, but still is not good enough to actually not be just overwhelmed by this muons, right? So that's why we have the outer veto here. These are pretty interacting, so these muons will give you a signal also in the outer veto, so we can actually very safely say, okay, wherever you have a signal, both in your liquid argon bath here, the outer veto, and the inner detector, this is not dark matter. So you can see clearly now how the outer veto in DARSAI 20K is actually fundamental to do any kind of search, dark matter search in this experiment. Here at the UCR, we are leading the design of the outer veto. This is a drawing done by one of our undergrad students, Sarah. And also, we are currently doing a lot of R&Ds in our lab to test the materials for this outer veto. So Alec, our senior grad student, will tell more details about Reflect, to test the reflectors. Also, Jared built this dark box here to test the eyes in DARSAI 20K, the photosensors based on semiconductor, silicium, with the Wide Eyes project together with Andrew. But also, you want to test this guy also at a very cold temperature, the argon temperature, 87 Kelvin, if you're wondering, and you need something like that, a cryostat. And we are going to do more tests, also testing things like how much the reflectors shrink at a cold temperature in the project called R&D. Now it's 7 months since I joined the Shawn group, and I'm very excited to have all these undergrad students working in our lab. They are very enthusiastic, so the reason why this lab is proceeding so quickly is also because we have these students happy to contribute. Here we have the neutron detectors that we count to build in the future. These guys will allow us to test measure the backgrounds for Dune, do some very interesting calibration for future dark matter detectors. This is the distillation installation that one of our grad students, Nika, together with the Sidra undergrad student, they are building in the fume hood with the television project. All of this will allow us to have a unique sensitivity to the signals from our universe, not only about dark matter in itself, which is the main aim, but also neutrinos coming from a eventual supernova. Actually, UCR is also leading the multi-messenger physics program in DARSAI 20K. We are also, I am personally mentoring also students, not only in our university, but also in other campuses, interested in seeing how DARSAI 20K can see for these neutrinos from rare event. So we are sensitive in DARSAI 20K to any neutrinos coming from any supernova exploding from where we are, hopefully not so close, up to the Large Magellan Cloud. This is very important also for what was told just before about interacting with the researchers from other field. That is an example of supernova are actually very interesting because most of the most of the energy is released by neutrinos, and we can inform telescopes and gravitational wave antennas. So gravitational wave, as far as I know, can in principle detect LIGO can in principle detect gravitational waves from supernova, but they really need pointing information and timing information. So that's what we can help. All of this is possible because we are very cool with argon. We can have a great sensitivity to KV energy deposit. But then the question is, okay, how can you go from here to here? There's a river to cross. That's not just something that you can get just scaling into bigger detectors. You need to do something different. You need to change your paradigm and actually change your target. Add a few dopants, a few percentages. Just not argon, just have a few percentages of xenon, alene, photosensitive dopants, which essentially will enhance the light from the argon itself. This is a nice drawing done by Sarah of the detector that we are going to use for this, loaded, which will be inserted here in our big cryostat. If you visit our lab, you're going to see just in front of our circulation purification system, which was assembled in February. And if this works, if we have a mixture, a stable mixture of argon together with some dopants, stable, easy to scale, this will be the target for dark side low mass, giving us a unique sensitivity for dark matter, which was never searched so far. And now I will give you the word to our senior student, grad student, Alec.
Thank you, Michaela. So hopefully by now you've been convinced that we have a lot of big and mysterious open problems in physics that we're trying to address and some ambitious plans on how we can address those problems. So I'm one of the lab monkeys that does some of the day-to-day work to actually accomplish those goals. And so for the last few minutes, I'd like to give you a little bit of an idea about how that's done. So pictured behind Dr. Westerdale and myself here is the giant shell that holds DarkSide 20K, the system that we just heard about. And as you can see, it's huge. And so if you want to develop such a large detector, then we need to build a small or relatively small scale prototype, which is what we have here in the lab. Note that it's still large enough for me to easily crawl inside. But this is the cryostat where we'll be testing our xenon-argon doping system and expanding on that. But if we want to really push the boundaries of knowledge in terms of dark matter, not only do we need to be able to detect these very faint signals, very rare signals, but we also need to do it with these huge detectors, the size of a room, as we saw. And this is very much like listening for a quiet sound in a very loud room. And so this setup right here, the reflect setup is where we'll do some of the testing of the materials that we're going to design this detector out of. Because as you scale to larger and larger detectors, the techniques that worked for those smaller detectors simply become unstable. And so in this setup, we're able to inject light and then read it through just a single photosensor. And when I look at this, I'm always reminded of like a cybernetic implant. But using this, we're able to turn those microscopic interactions into something that's macroscopically observable. And very much like the pulses on a heart rate monitor, we can see pulses from individual photons, just single photons, appearing at our sensor here and get very high precision measurements. The other piece of this puzzle is the simulations that go into doing this. Because we not only want to be able to predict what kind of signal the dark matter is going to leave in our detector, but we also need to be able to model all of the standard or expected interactions, so that way we can see exactly what we expect to see and then look for any deviations from that. So on the left-hand side, some work also done by our undergrad Sarah Howick is engineering the electric field which will actually be in place inside of our detector. And on the right-hand side is a simulation I've done of that 250-ton argon bath, which will surround the DarkSide 20K detector. So I'd like to finish off by sharing with you the logo that was designed by the 2023 P5 Commission. This was a national effort panel that laid out the plan for particle physics over the next 10 to 20 years. And on one end of the scale spectra, we have the quantum realm and deciphering its mysteries. In particular, our lab is working on those elucidating the mysteries of neutrinos. And on the other end of the size scale, we have the entire universe. And we want to illuminate all of those invisible and unknown mysteries about it, in particular, determining the nature of dark matter. And the labs that we have here in Riverside sit here in the middle, exploring new paradigms in physics, in particular in our lab, in the Westerdale lab, the search for direct evidence of new particles. And so I can say with good confidence that the work that's being done here in the experimental cosmology labs is certainly pushing the frontiers of new physics. Thank you for your time.
Thank you, Dr. Shawn Westerdale, John Richardson, and Steve Choi, and your group members. Special thank you for Dr. Barry Barish. Thank you all for joining us in celebrating Dr. Barry Barish's award and for sharing this very exciting and special moment in your department with the creation of the center. Okay, I'm going to call Vice Chair of our department, Rich Settle. We still have a little bit of time for a quick...
So on the advertisement, we were going to do some lab tours, which we're going to continue with, although there's not much time. So what we'd like for the people at lunch who are going to go on the tour, please, as I said at lunch, meet us on the right there, right of the theater. For everybody else, there should be a bunch of students that are waiting for us right in the back, and Owen Long will be taking us out. So please, for those of you who are interested in the tours, move right out, and I'll meet you out, the people at lunch, I will meet you out there in just a couple of minutes. Thanks.